The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi there. Welcome. I'm Brian Spatocco, and we're going to be going over Exam 2 from the fall 2009 semester. The logical place to start on this exam is problem 1. And what I usually do for all the problems is discuss the things we need to know before we start it. So I would recommend reviewing these concepts before attempting the problem, and then attempt the problem, and then identify your weak spots. So here's what I personally found to be important information to know before attempting the problem. So I call it what I need win, if you want to win. There's 4 things. The first are Miller indices. This is a way, this is a crystallographic notation for figuring out and communicating planes and directions in crystals. So review Miller indices. We have plane direction notation. I'll explain a little bit more what that is in a second. Definition of planar density, and for that matter, linear and 3-dimensional density as well. And 4, the concept of a crystal basis. And this is actually the concept that most students had trouble with on this particular question. So those are the things I would recommend you look at before starting. And if you haven't, check it out now. So let's start off with problem A, part A of problem 1 rather. And so the question asks us to draw the crystallographic feature indicated and label it clearly. It doesn't actually say if we're drawing planes or directions, and that's left to the exam taker to identify. So the first thing I note on that problem, part A, is that we're asked to draw 0, 1 bar, 2 bar, and 1, 1, 1 bar. So the first thing I notice about these 2 particular crystallographic features is how they're actually encapsulated. So the first one is in parentheses, the next one is in square brackets. And that actually tells us some information about the problem. The first part, A, part 1, is 0, 1 bar, 2 bar. So you actually need to know what this implies. Parentheses mean we're looking at a particular plane orientation. Now I'm not saying a plane, I'm saying a plane orientation, which means there are infinitely many planes in a crystal which have this orientation. Okay, so that's distinguishing between just one plane in a crystal. The second part, B, we have square brackets. That implies we're either looking at a direction or a place in a crystal. We also have things like this, which we're not seeing on the exam this time, but may show up later. We have these curly brackets, and we have these angled brackets. The curly brackets denote a family of planes, and the angled brackets denote a family of directions. And that's markedly different than a particular plane direction or plane orientation and a particular direction. So let's do some visuals here to explain what we mean. So let's start off with A1. And we're asked for 0, 1 bar, 2 bar. Now, the bars indicate negative signs. So you would know that from your Miller indice review. Now, the way to do this problem that I find is the easiest, the way we reviewed in recitation, was to not be afraid to move your origin. A lot of people are afraid to move their origin around, but we have to remember in a crystal, basically what a crystal is, it's a unit lattice repeated infinitely in 3 dimensions. So it's okay to move your origin, as long as you choose some reasonable point. So in this problem, we're looking at the back bottom left corner. That's our defined origin on the paper. But to do this problem, I would recommend choosing a new origin. I chose this one. And that's really going to facilitate doing this problem a lot more easily. So let's look at what we have to draw now. 0, 1 bar, 2 bar. The 0 indicates that we're never actually intersecting the x-axis. Okay, so at no point will this plane, we know it's a plane because the parentheses intersect the x-axis. The 1 bar indicates that we are intersecting the y-axis at 1 lattice parameter spacing. Okay, so Miller indices are a little tricky because they're somewhat inverted. 1 implies you're going the full distance of the unit cell. 2 implies you're going half the distance. 3 implies you're going a third the distance, and so on and so forth. So for 1, we're going to go the distance of 1. Okay. We're going to move -1 in y. So we're going to move -1. We're going to go to here. That's in our y. And let me make this a little clearer. I've chosen a new origin. So here's my y prime. Here's my z prime. Here's my x prime. So we're moving -1 in y. We're going to move -1/2 in z. Okay? And we're also told that this plane doesn't intersect the x-axis, so it must run parallel to that axis, which tells me that it's going to run along the x-axis, and we're going to get a plane like this. And here's our plane. That's the answer to part A1. Pretty easy, and most students got this correct. For part A2, we're asked to draw a direction or point to a particular place in space. I also moved my origin on this problem, and I found it easiest to redefine my origin up here, which means that my new set of axes are going to be x prime, y prime, and I'm going to keep z because z didn't move at all. Okay, now note how when I'm drawing these things, we're going to draw this one now, that the way I choose to move my axis, or my origin rather, generally tracks with the negative signs that I have. So in this problem, I had a -y and a -z. I moved in the -y and -z directions. Here I had a -z, so I just moved up in the -z. That kind of told me how to move my origin. It made life a little easier. And now it's pretty easy from here. Now what we're going to do is draw 1 in the x, we go 1 in the y, we're going to go -1 in z. We're pointing to this point. There we go. That's our direction. So pretty easy. Part A1, part A2. So we're batting 100 right now. And just don't be afraid to move your origin. That's the takeaway from this part. The problem, of course, gets a little harder. That's something that we pride ourselves on in 3091. If it was always this easy, everyone would pass the class and get hundreds. So the second part, part B, is asking us to calculate the density of atoms in a plane. So this gets back to what I was saying before. We need to understand the definition of a planar density. Okay, so I've sort of defined it here. This is rho, not p, rho planar. Okay, and rho planar I define to help me, maybe it'll help you, is the number of full atoms in a particular plane. In this case, we're looking at 0, 0, 1, divided by some area, because a plane is denoted by an area, not a volume. Don't be afraid. I mean, densities don't always have to be mass over volume. It can be some thing, some unit over some specific distance or area or volume. So that's general density. So we're looking at the number of full atoms in a plane divided by the area. We're told that we're looking at dolium, of course named after Salvador Dali. And so we're also told that we're looking at the 001 plane. I've drawn a BCC crystal here. As a scientist or an engineer, when you're given BCC, FCC, simple cubic, the first thing you put on that paper is the actual crystal structure. So I drew the dolium up here, not a real element, but a make-believe one. And we're going to identify our 001 plane. This is good practice. So here's our x, y, and our z's right here. Our 001 plane. So we're not intersecting x. We're not intersecting y. We're only intersecting z. So here's our 001 plane. Let me sort of bring this down for you so we can look down on it from above. It's a square with sides A, okay? And here's our atoms. Okay? So now the question is, how many full atoms do we have and what's the area? Well, the area is obviously A squared. And the number of full atoms in this area is we have 4/4 of an atom. When you're in two-dimensional space, an atom looks like a circle to you. When you're in three-dimensional space, it looks like a sphere. So if you lived in the two-dimensional plane, you would see 1/4 of an atom, 1/4 of an atom, so on. You'd have one full atom in this plane. So this is sort of what we're looking for. And you say, oh, well, I'm done. And a lot of people left it at that. But that's not the answer we're looking for. We want an actual numerical answer. So the question now becomes, well, what is A? So we're going to digress and find A, and then we'll know exactly the answer to the planar density. So A, this is where you have to be a little clever. How do you find A, the lattice parameter, the lattice spacing? So the best way to do this is to think both small scale and large scale. So first, let's think about a unit cell. let me ask you, what's the three-dimensional density of a unit cell? So how many atoms do we have per unit cell? We have our BCC. We know in BCC there are 2 atoms. We have 8 corner atoms, and they're each an eighth. We have 1 body atom, so there's 2 atoms. So we have 2 atoms per, what's the volume? Well, the volume is A cubed. Now, so now we got A cubed. We didn't really make any progress here. We still have an unknown variable, but the question is, how do we get solved for A cubed? So let's zoom out from that unit cell. Let's zoom out to a mole of material, okay? So a mole of material, how many atoms are in a mole of material? Well, by definition, it's Avogadro's number, 6.02 times 10 to the 23rd. And then, what's the volume of a mole of material? Well, looking back at the problem, we're given the molar volume, which is something that I would recommend you write down, all the information you're given, see what you've got. The volume of a mole is the molar volume, which we're given. So now it's pretty easy. We know Avogadro's, we know molar volume, so we can solve for A. Okay? So not too bad. You'll find that A is about 2.8 times 10 to the negative 8 centimeters. Okay? You could give me 2.85, 2.79. We're worried about the concepts here, not the numbers. So don't go back and waste a lot of time getting the exact number. That's our A. And now that we've got A, we've got our planar density. Very easy. I'm going to write rho plan, just to save some time. And that equals 1 over this number squared. That's 1 atom, by the way. And that's all squared. And we're going to find, in the end, that our planar density is going to be equal to 1.27 times 10 to the 15. And the units are important. That's atoms per centimeter squared. Okay? If you don't give us the units, then we have no idea if you're right or wrong. So always include your units at the end. So hopefully that helped. We're going to take a second to clean off the boards, and we're going to start with part C. Okay, we're back. We're going to finish problem 1 now from the 2009 exam 2. We're on part C. So thus far in part A, we've talked about Miller indices. We've talked about the plane and direction notation with the parentheses and the brackets. We've also talked about planar density, and I would invite you to review those things. Now we're going to go to part C, which is really the concept of the crystal basis. And this was the part of the problem that most students lost points on. So it's the thing that I would emphasize the most on this problem. The problem asks us to, and I put a sad face because that's how people felt after this part. The problem asks us to draw a particular plane in an FCC crystal. So we're given magnesia, MgO. They want us to draw that plane and show the atoms. And they also, we also want you to show the relative sizes of the atoms. We have anions and cations. And we actually give you the sizes of those ions, so it shouldn't be too tricky on that part. But I think the best way to start is to go over the answer that was given that was wrong. And then we're going to talk about why it was wrong and how to get the right answer. So you start off, we want you to draw this crystal. The best place to start is by actually drawing the crystal in 3D, and then we're going to take the projection after that. So people think MgO, they see FCC, and they say, oh, that's not so bad. I know what FCC looks like. Let me draw FCC. And I'm going to use, for this problem, I'm going to use this red chalk to represent magnesium and the blue chalk to represent oxygen. Okay, so magnesium, we're going to have it as a circle like this, and this is magnesium 2+. And we're going to have the oxygen, it's going to be slightly bigger because it's an anion. This is O2-. Okay? Maybe, maybe I'll color this in too. People said, okay, easy. FCC, this is a simple problem, easy points. So they drew what they thought to be an FCC crystal. So they did, let's say they put the MGs on the corners. And they said, oh, okay, well now I need my faces. So maybe the oxygen are the faces. So I'm going to put in my 6 face atoms. So here are my 1 in the side here, and I got the bottom and the top. There's my 6 faces. They said, oh, okay, easy, I'm done. And then they took the projection of 0, 0, 1, 1. We know, and we also know, let me put the axes on here just to make it clear. And here's our z. 0, 1, 1, we know it doesn't intersect the x, but it intersects the y and the z at one lattice spacing. So x doesn't intersect. It intersects, z here, intersects y here. So we've got this kind of plane going on here. You've got something like this. And then they just drew this. It's a little bit of 3D visualization, but they drew that and they got 0 points. The reason that is not a correct answer is because that is not what MgO, it's a rock solid structure, it's not what it looks like. And because the reason they got it wrong is because they didn't understand the concept of a basis. So I'm going to make a statement right now. This is a really important statement, so I urge you to think about it. A crystal equals a lattice plus a basis. Here's the difference. A lattice is a collection of points. So you have an FCC lattice, you have a BCC lattice, you have a simple cubic lattice. Those are points where atoms, and I use atoms plurally perhaps, can exist. Okay? A basis I like to think of as a stamp. A basis represents the most fundamental pattern that you stamp at every lattice point. So let's draw an FCC lattice. Okay? So I'm going to draw an FCC lattice down on this cube right here. I'm going to put points. So I'm going to make them white. They're just points. Okay? I got all the corners. They're hard to see, but they're all the corners. I got the faces, side, back, front, and bottom. Okay? And you're saying to yourself, hey, it's like the same thing you just drew. It's not. What I drew the first time, I put atoms in. Okay? That's a crystal I drew. I just drew a lattice right now. This isn't a crystal. This is a lattice. So to actually answer the question, we want to draw the 2D projection of a crystal. So we've got to draw the crystal eventually. Now, we're dealing with MgO. We're told MgO is face-centered cubic, which means that our basis must have one Mg and one O atom. So I'm going to do that right now. I'm going to draw what I'm going to call to be my stamp. You can use whatever method you think is best, but I call this my stamp. I'm going to draw it like this. Go. So here's an oxygen atom, here's a magnesium atom, and this little white dot is where that's the point that's going to get stamped. And here's my stamp. And the idea is that I'm going to take this stamp, this basis, that's what it is, it's a basis, and I'm going to stamp it at every lattice point. Okay, so note I have 8 corner lattice points and I have 6 face lattice points, so I'm going to be stamping 14 times. So just to give you, I'll do the first couple very slowly. I'll take my stamp, and I'll stamp here. Here's my O. Here's my Mg. I'll stamp over at this corner. Here's my O. Here's my Mg. I'll stamp in the face. Here's the face, the front face one. Here's my O. Here's my Mg. So you can see what's happening. Let me circle it for you. I'll circle one of them. Here's my stamp. Okay? I'm going to go ahead. I'm going to finish drawing this in. It's going to get a little messy for a board, but I hope that you can go home and do it with some graph paper as well. All 4 corners, faces here. I have a tendency to leave off faces sometimes and make sure I've got them all. Oh, I already did that one. Okay. Oh, no, there we go. That's fine. Okay. Yep, that's right. Is that right? No. There we go. Okay, and let me finish with the magnesiums. The magnesiums are going to exist. It's going to be hard to see, but they exist at the center of every edge. Okay? Okay. So it's a little tricky, but let me explain what we're looking at, what you should be looking at. We have what looks to be oxygen in a face-centered cubic arrangement, and we have magnesium at all of the edges. Okay? So you're thinking, oh, this is weird. This isn't face-centered cubic. Look at the magnesium. This doesn't look face-centered cubic. Well, the thing I would challenge you to do at home is to actually draw this unit cell out 4 more times, and then you will actually be able to find, you'll be able to find a face-centered cubic magnesium lattice cell in that larger lattice, or unit cell, sorry. So this is actually the answer. This is what a rock salt structure looks like. This is MgO. You have oxygen that looks like your traditional face-centered cubic, and you've got these magnesium stuck on all the edges. So now we're just going to take our projection. Let me use white chalk for that. Or rather, we're going to take our plane. We're looking at the 0, 1, 1 plane. Here's our axes again. Remember, it's always right-handed. Z. We're going to do 0, 1, 1. Not intersecting the x, and we're going to intersect z and y. So we're going to kind of come down across the face. And we've got this. Now this is kind of, this is pretty terrible looking, but this is one of the tricks of the problem. You have to be able to visualize these in 3D space. So let's slowly transcribe what this plane here looks like projected out on the board. We know that at our corners and also at the faces of this cube, we've got oxygen. So here's a corner. These are our corners. Okay? And at the faces, 2 faces, we've got oxygen. Okay? What do we have? What else do we have? We know we must be hitting some magnesium. Well, we know that at all the edges, here's an edge and here's an edge, we've got some magnesium. What about the center? Well, the center we do too, because we know that when we made this stamp, the bottom face with this oxygen, we also stamped halfway up a magnesium. So there's actually magnesium right here. It's there. It's right there. Believe me. There's our magnesium. Okay? And this is what we've got. This is the answer to the problem. Notice how I've given my oxygens larger than my magnesiums. Sorry. And I've got it looking like this. You know what? In fact, let me emphasize this even more. The fact that you could actually have drawn this differently. You could have drawn it like this. And it would have been exactly the same thing. You would have gotten full credit. You could have drawn this. And this is the thing that I would recommend you go home or you try and you're at home to prove that this is true. These two are equivalent. It's the same thing. It all depends on what you choose as your stamp point. Okay, so I could have chosen to put my red at every point, my magnesium, but I didn't. So this is the answer to part C. This part most people did not get correct. Less than half of the class got this correct. So think about it a little bit. Identify crystals, lattice plus basis, and then think about the full scope of the problem. What did we go over? We went over Miller indices, went over designation and crystallographic notation, so plane and direction notation. We went over the definition of planar density. Think about what linear density means. Think about what 3-dimensional density means. And don't be afraid to not use mass. And the last thing we just covered was the crystal basis. So review those, and hopefully you did well. Thanks.